I was going to try and get a recording of it. All right, so let's talk about color first, because light and color are intertwined. So, what happens when you mix colors together? Yeah, does it get darker or lighter? Darker, right? On paper, but here's the tricky thing, and this messes people up every year in this class. We talk about what happens when you're using paper, right? Like painting, but it works a little bit differently with light. Because the more color we add together, the closer we get to white light. So if I take my primary colors here, and we've been told red, yellow, and blue, but really for light, like our monitors, you'll see them called RGB monitors, right? So that's red, green, and blue. So let's see if I can get this a little closer here. When I put these three colors together, if I get them in the right frequency, see I have a little bit too much red and it's kind of yellow, but if I back that off a bit, what are you seeing right in the middle? On the garbage? White. Yep, white, right? So this works in reverse from what we're used to doing on paper. The more color we add in, the closer we get to white. Notice when they light up, or when they line up perfectly, we got white. So what our monitors are really doing is the more colors it's adding in, or our camera sensors as well, anything that deals with real light, not reflected light. The more color we're getting, the closer it is to white light, right? So we call this additive because we're adding colors together to get white. But subtractive is what we're used to seeing on paper, right? Because we're removing wavelengths of color. We're taking away maybe red or blue. And that's how we get color on paper, because paper works by absorbing light, right? It's going to absorb all the colors except for blue, so we see blue. Whereas out here in the real world, when we're looking at reflected light, we're seeing the actual light wave bounce off of something, right? Does that make sense to everybody?
So you're seeing a blue light wave bounce off, let's say, a wall, wise?
Yep. And you'll notice in photos too, you can get a color cast just from, if I were to put a red balloon by that white board and have a lot of light bouncing off the balloon, the board will actually have some red on it. And not just from being kind of transparent, but because colors can be reflected with light when we're talking about light. But paper works the exact opposite way. So if I print red ink on a piece of paper, it's going to absorb all the light rays except for red. So the only one coming back to my eye is red. Yeah, now in the real world out here, we have actual red light and that's what makes red. But when we're talking about paper, we're talking about it absorbing every color except for red. And that's why you see it. That's why it's subtractive. It takes away other colors. Does that make sense to everybody so far? Okay, now we'll talk more about color later because we have that chapter coming up in our book, but these things are kind of intertwined. So let's look at what our lens does. Now you could poke a hole in a box and make a pinhole camera, which we'll be doing soon, and it doesn't use any glass or any sort of lens at all, right? And it can take a picture, but the problem is it collects light rays so slowly through the tiny pinhole that it takes 20 minutes to take one picture inside here, like in this room, right? It's just not practical, so what we started doing was making lenses. And we have convex and concave lenses. So these lenses are going to do different things. Let me see if I can move that a little bit. All right. They might push light in a certain way, but we are controlling how light bends. Can everyone see that bending a little bit? And we have ones that kind of dip in like this and ones that go outwards, right? They all do different things. So the ones that go outwards are going to collect light and bend it together. And the ones that go inwards are going to split light. So let's see what happens if we use a concave lens. Can everyone see what it's doing to the light rays there? Do you see them bending outwards? So in real time here, we can see how this lens might affect it. Let me see if I have a thicker one. Ah, here we go. There, you're really going to see it. Now, if you have a lens like the one I had, that big white one, that's going to use a whole bunch of lenses. There's probably about 10 lens elements in there, and it uses them to push light in certain ways. So here we're splitting the light rays apart and then bringing them back together. So when you focus your lens, what you're really doing is grabbing all the light that's out there and you're bringing it to a point. So that point of light, does everyone see it on the bottom? That's that point of light that we're talking about that is all important in your camera lens.
The top of the triangle, so to speak?
Yeah, right where it comes to a point down there, because we're bending all the light that's out there in the scene around us into a point. And so that point is our focal length, from where light comes to a point to our film or sensor, right? That distance is your focal length. But what we're really concerned about is we're grabbing all the light in a scene and we're basically sizing it to hit our sensor perfectly. The reason we have lenses is because of speed, for one thing. So the pinhole camera takes 20 minutes in this room to make an exposure, right? Now this, because we can grab a lot of extra light rays out here and still focus them to fine points, which gives us a detailed picture, that allows us to take pictures with the shutter speeds we use. And what's the fastest on our camera? Anyone? Sophia? What's the fastest shutter speed on your camera? What's the fastest you've gone to?
30 seconds.
You can go up to, well, like, think about the cars.
Or
Like,
fastest.
yeah.
I was confused. I don't know. I'm bad with numbers when it
Probably like what, 1/2000th, I think, 1/500th at the very least for that worksheet. So we can split a second up into, say, 2,000 or 4,000 pieces, right? So quicker than we can blink. So this allows us to get so much light brought in that we can have very fast shutter speeds. If we did not have this ability to focus these light rays here, we'd have to wait 20 minutes per picture. Right, so the whole reason we have lenses is that we can grab all this light, bring it into the camera quickly and efficiently, and then we get this very fine point, which also gives us very fine dots on our final picture, right? This is resolution, in a way. So our lenses are usually bending the light in a lot of different directions, outwards, and then maybe back in, etc., focusing it to get the point to land right where we need it to land. And we're going to see the same thing with lasers here. We talk about the term refraction. So what refraction really means, if you look in our book, is it's when light goes through one transparent medium to another. And every time it goes through a transparent medium, it's going to bend once. So that means if it's going through the air and hits a glass and then clear water inside, has anyone ever seen how water glass looks really contorted on the inside? Like everything bends around the inside, right? It's because it's refracting two times. It's going through the air, one clear medium, it's hitting the glass, another clear medium, and then going through the water, another clear medium, and then plus out the other side, right? So whenever it transfers from one clear medium to another, it's going to bend. So let's look at my crystal ball here. I see all A's in the future. We can bend light along this ball. So notice I have it at a right angle to the ball, but that light is going down at an angle from here. It's going down the ground, right? It's going in a completely different angle. I'm going to try not to shine this in Mr. Schaaf's eyes here. Completely different angle from where it's hitting this ball. Bending almost at a full 90 degrees difference from where it should be coming out the other side, right? And we have all different shapes that we can see this with. If I shine this through here, it's not really coming out from the other side. It's kind of bouncing back because it's hitting it directly, but the angle does matter. You'll notice as I go around the sphere, it's going to change where it comes out. Same thing with this. When I hit one of these crystals at an angle, it's completely bending an angle. So you'll see it goes in at this angle and exits at about the same angle. So the angle light hits it really does matter, depending on the direction. So what we want to experiment with today is seeing how light bends. So I have a worksheet.
Light benders.
Yep. I have a variety of crystals, convex lenses, all sorts. Oh, one more thing I want to show you before we get to that part. Just another illustration of light. So when I say that light is a ray, it's also a ray and a wave, and there's a little video we'll watch on this. Now this isn't physics class, so we don't have to delve too deeply into it, but light functions both as a ray and a wave. And so if you've ever heard the term quantum physics, this is what it refers to in a basic sense. Light should be either a ray or a wave, kind of like ripples in a pond. But it behaves in two different ways, and it depends on how they've observed it before. So they're observing shooting light through two slits in a board. And the light should just go across, hit the board, bounce off, except for when it goes through a slit and leave two photoreactive areas right through the slit, right? But they found out it actually rippled out. When it hit the slits, it made ripples, kind of like a pond. And whenever a ripple hit another ripple, it would change the wave. So it was hitting the backboard in all sorts of areas instead of just their two slits. But sometimes it behaved as rays, where it would go right through the two slits and only leave a mark on the photoreactive stuff there. And sometimes it would react as waves. So it's really a mystery at this point. And the weirdest part was, it seems like when they observe it, light changes how it acts, which seems impossible, right? Light doesn't know when you're watching it. But it's one of those mysteries that they're trying to figure out right now. But light is both rays and waves, so it's kind of dim here, but you can see this light spreads out. And this is sort of how it acts as a wave. It's going to spread out like a ripple. But this is also what our lens does. If our light kept spreading out, we would get very soft images, right? We want sharpness. So that's also where our lens helps us. Notice it takes all these waves that spread out and soften as they go out further, and turns them into a perfect sharp point, which is exactly what we want our camera lens to do, right? A very defined point, so we get very sharp, clear images. Before we proceed, does anyone have any questions about that thus far?
Mr. Wise, are we learning about lenses?
Yes, we are. Yep. Alright, class, so let me divide these out, and what I will do is get a few lenses for each group. Now we're going to do groups. Let's go ahead and have you 4 there, since we're missing a few people. You 3 and Miles, and then this group here of 4 is a group 2. So I'm going to set these out so we each get a few. And we're going to experiment a little bit with lasers. I have a worksheet here. Now we had a few copyright issues today, but I think I have enough for everyone. So we just wanted to see how light is going to bend and refract. You'll see a few drawings in the back of this. And all you need to do for me on this is detail how light is going to bend through the different lens shapes that you see here to figure out what our lenses are doing. So I'll turn the lights on so we can take a look at these real quick, and then we'll get everything set up, turn the lights back off. You're going to want to recreate some of these lens configurations that we commonly have used with lenses like what we have. This hall, we always turn each other's lights out by accident. Okay. So we're going to have one station here that has the globe. A couple of these prisms to try. We have what we call a convex lens. And so convex means that it bulges outwards on both sides. This is used to gather light. Then we have concave. This one is going to spread light apart. We have a lot of other shapes too that aren't really used quite as much on lenses here, but they're used in optics in general. Some things we can experiment with today. We have prisms, of course, which are triangles. Now those aren't used in cameras, but it is interesting to see how light rays will bend around them. So you'll notice in those illustrations there that you have some convex and some concave. So each of these sets are matched to fit up. And we have these lights as well as 3 lasers.